Hey everyone, this is Mr. Geiselman here to talk a little bit about gravitational potential energy. So we're on to our last leg and some of the last stuff that we're going to cover here in PS9A. So hopefully you're keeping up to date, making sure all your stuff is in. So let's talk a little bit about gravitational potential energy. So what is gravitational potential energy? It is the energy that is stored in an object due to gravity. So where it is in relation to a reference point or how high off the ground it's going to be. The higher off the ground or higher off of that reference point, the more energy it's going to store in it because the force due to gravity is always pulling down on it. So it's going to have some energy in it that is related to its height, right? So it's always based on the object's position. The higher off of that reference point or the higher off of the ground the object is, the more energy it's going to have. And it will take some work to get that object off of the ground. But like what we've noticed in work and energy, they're related. So to get more energy, you got to put in some work. Our unit for gravitational potential energy is the same as work. We're measuring this in joules. So energy is measured in joules. So it makes sense that gravitational potential energy is also measured in joules, right? And the potential part of this phrase, gravitational potential energy, it has the ability to do work. At this point, it isn't doing any work, but it has the ability to do some work. And our equation is potential energy, in this case, gravitational potential energy, is equal to the mass of the object times the acceleration due to gravity, g, and times the height. So the equation is mass times gravity times height. It's a pretty simple one that we're going to get to here in a few slides. So when we look at it, that equation mgh, mass is equal to the mass of the object. And obviously, just like the entire trimester before this, we measure mass in kilograms. So we're going to get a mass in kilograms multiplied by an acceleration, right? A meters per second squared. And this is the acceleration due to gravity. Here on Earth, it's 9.8 meters per second squared. If we were on a different planet, we'd have a different gravity or acceleration due to gravity, excuse me. But here on Earth, that number is always going to be 9.8 meters per second squared. And then the h obviously stands for height. We measure height in meters. So it's not going to be in centimeters. It's not going to be in inches. It's going to be in meters. And it's always to a reference point. It could be the ground, or it could be a tabletop, or it could be something different. So when we're measuring that reference or that distance, that height, it's going to be a reference point. And we'll see what that looks like here in a little bit. So here's a practice problem that I'd like you to try and solve using that equation, mass times gravity times height. A baby carriage is sitting at the top of a hill that is 21 meters high. The carriage with the baby is 12 kilograms. First off, determine, does it have potential or does it have kinetic energy? Fill in the variables that are over here. Fill in the variables that are missing over here. We have mass, height, gravity, and then velocity. Write the correct equation here, whether it's for kinetic or for potential gravity due to, potential energy due to gravity, and then substitute and solve over here. So I'll give you a sec to figure this one out. What is the energy of that carriage? So hopefully you figured it out that it's potential energy because the baby carriage is sitting at the top of a hill. It's not moving. So the very first thing there, pretty easy, 21 meters high. Well, only one of our variables requires a distance, and that's height. So 21 meters goes there. The carriage with the baby is 12 kilograms. Only one of our variables is measured in kilograms, in mass, right? So mass obviously has to be 12 kilograms. And it doesn't say that we're on another planet, so it's pretty safe to assume that we're on Earth, and that's why acceleration due to gravity, or g, is equal to 9.8 meters per second squared. It doesn't give us a velocity, and that's fine. We just don't use it. Velocity would only be used in kinetic energy problems. So obviously it has potential. So we write out our potential energy equation: mass times acceleration due to gravity times height. All of those numbers are there, and I did a bad job. I did it a bad example because I didn't put the labels here. But this would be 12 kilograms, 21 meters, and 9.8 meters per second squared. And when you multiply all of those together, you get our answer of 2469.6 joules. Right, 2,469.6 joules. Let's try another one. So with gravitational potential energy, I mentioned earlier that the height is to our reference point. So in this case, we have a piano and a ball on top of a building. The height here says it's 15 meters, but our reference point is the ground. So that's what I'm saying when I say a reference point. In this case, we know for sure that our reference point is the ground. So we can start solving for our potential energy because we have mass, we have height, and we know it's on Earth, so we know it's the acceleration due to gravity. Let's start with the piano. So the potential energy formula is right there. PE equals mgh. And for the piano, we know that the mass is 150 kilograms. We know the acceleration due to gravity because it's here on Earth. And then it tells us the height right there in the problem. So we're able to figure out by multiplying all those numbers together, that we get an answer of 22,050 joules because energy is measured in joules. We'll do the same thing again for the tennis ball. We'll use mass times gravity times height. And for this one, gravity and height stay the same, 9.8 meters per second squared and 15 meters, but our mass now changes to 0.06 kilograms. So with the tennis ball, we're going to get a much smaller number because there are much smaller energy value because the mass is much smaller, right? And we get an energy or a potential energy of 8.82 joules. If you can imagine, would you rather have a piano fall on you from 15 meters or a tennis ball? Right? You'd rather have the tennis ball because it will do a lot less work, right, when it hits the ground. It has a lot less energy. So that's it for